Right. So first off, thank you very much for allowing me to give this talk. So my name is Hunter Gabbard. I'm a PhD candidate at the University of Glasgow. And today, I'm going to talk to you about some work that myself and several other colleagues, both the physics department and the computer science department at the University of Glasgow, have done, where we've shown for the first time that we can use a form of machine learning, not vanilla conditional variational autoencoders, but a variant of that, to produce Bayesian posterior parameter estimates for gravitational waves. So a brief overview of the talk. So first off, I'll go into some motivation for why we do this work. Then I'll talk a bit about what conditional variational autoencoders are, and of course, the particular variant of that we use, talk about what we did, and then given those results, where are we going to go from here? So motivation. So once you detect a signal, you want to try and get some of the physics out of that signal from a gravitational wave. You want to try and extract some information on the source parameters of that signal. So for example, the masses, how far away it was, et cetera. Currently in LIGO, the best way to do that, or the way that we normally do this, is using something known as Bayesian inference that you're all probably very familiar with now. And also, as most of you know, Bayesian inference is the optimal way to do this, but it's very slow. And as we upgrade the detectors and we start seeing more and more events, not just one or two every year, but rather hundreds to thousands of events, and taking into account the fact that for the most recent observing run, it took anywhere from of order at minimum 6 hours to get full Bayesian posterior estimates from these signals, all the way up to about 5 days, right? And imagine you have hundreds or thousands of these signals coming in your detectors at once. This is going to be a massive problem going forward. And we want to try and also alert our other electromagnetic observers in as quickly a manner as possible to tell them where to point their telescopes in the sky. So this is a big problem going forward. And so the question is there a way to solve this problem? We think yes. And we think it's conditional variational autoencoders. And I promise it's not magic. So first off, if I'm going to describe what a conditional variational autoencoder is, I should first go into detail about what an autoencoder is. So an autoencoder, let's imagine we have, say, a set of MNIST digits, and we want to, given some MNIST digit, we want to try and reconstruct that digit. So an autoencoder is made up of two different function approximators. In this case, let's consider those function approximators to be neural networks. One of those is an encoder network. The other one is a decoder network. The encoder network takes as input one of these images and then compresses that image down into something known as a latent space, which is sort of learned numbers, which sort of take into account the most important aspects of what that image is. And then we have the decoder network, which then takes as input that latent space distribution and then tries to reconstruct the input that you gave to the encoder network. And your question may be, why is that useful? Well, the answer is not really that useful. But what is useful is what goes on inside the latent space, where you learn sort of the most important components of that image, right? So that's actually quite useful. So going from an autoencoder, so one of the downsides of an autoencoder is it's not necessarily a generative model, right? I can't just ask it to generate, if I give it to some random numbers from the latent space distribution, I'm not necessarily going to get back something that looks like an MNIST digit. So one way of trying to alleviate this is using a variational autoencoder. And they don't really change, you don't really change too much when you go up to a variational autoencoder. The only thing that really changes is that now your latent space distribution is represented, or your latent space is now represented as a distribution. So instead of getting the encoder to predict numbers from the latent space, you then try to get it to predict both means and distributions, which describe the distribution of the latent space. And what ends up happening when you go to train is that different parts of the latent space will correspond to different classes, say from an MNIST data set. But yeah, one of the downsides of variational inference is that, or sorry, not variational inference, variational autoencoders, is that I cannot ask on demand to return a particular class of image. So if I just do a random draw from the latent space distribution, what I'll end up getting back is something, some number from that MNIST data set, but it won't necessarily be the one that I want. And so one way of getting around this is by using a conditional variational autoencoder. So in this case, we still are representing our latent space as a distribution. We're learning both the means and standard deviations to describe that distribution. But now we're also given as input to both the encoder and the decoder a number which sort of describes what class that particular image is coming from. And now when I want to go and say I want like a 3 or a 4 or something like that, I then just give that as input to the decoder as well as the latent space distribution, and I can get back a 3 or 4, a 5 or a 6. So that's very useful. And this is sort of the tool that we use as most closely associated with the actual scheme that's implemented in our paper. You'll see soon that it's not quite a vanilla conditional variational autoencoder for what we want to do. So a brief overview of the analysis. So what we want to try and do is we're going to train on a set of whitened binary black hole time series in Gaussian noise. And we're also going to use the true scalar parameter values. We do not use posteriors during training, though we do produce posteriors during testing. This is just a few examples of some of the time series that we train over, ranging from a low SNR signal in the bottom and a very, very high SNR signal in the top right. We use about 1 million training samples. This is also for single detector, so we only use one detector. And we have about 256 test samples. Our priors are uniformly distributed. There's just some of those right there. We infer 5 parameters, though I will note that we marginalize over phase. It's not a particularly interesting parameter. Then we tune the network, and we produce posteriors. And we compare those posteriors with Bayesian inference using 4 different samplers. So 2 of those being nested sampling and 2 of those coming from MC. So this is really kind of just for posterity. So when you go back and look at the slides, these are some of the variables from our schema, which I'm about to show very soon. It's a very scary slide. But yeah, what we're trying to get is the posterior, P of x given y. Right, okay, so this is the scheme that we use. So the network that we use is actually derived from first principles. So you start from the assumption, so H right there, that you want to try and minimize the cross entropy between your true posterior, the Bayesian posterior, and some approximated posterior using this neural network. Then you do a bunch of very complicated math, and you end up with a loss function at the very end, where what's really nice and beautiful is that like different components of that loss function then correspond to the structure of the model that we end up using. So I've sort of circled which parts of that correspond to what, but log R sub theta of 2 ends up being your decoder network, which just also ends up being basically a mean squared error. The KL divergence term at the bottom ends up being 2 different encoder networks, where one is given just the time series, y, during training, and the other one is given both the time series y during training and also the true scalar parameters. And then when you go to testing, it ends up that you only need to use the encoder network that is just given the time series y, and then the decoder network will then output you samples from the posterior. And what do we find out when we actually apply this? Well, it's very, very, very fast and very accurate. That's also very important. So this is the money plot, I guess. So here we show our results in red for a single binary black hole, though we do other statistical tests to show that this doesn't just work for one test sample. It works across all test samples. But our results are in red. So we show 4 posteriors for 4 different parameters, gravitational parameters, that being the 2 component masses, when it happened, T0, and how far away it was, luminosity distance. And then we show, we compare to Bayesian inference for, I think this is dynasty, We also do this for 3 other samplers. And as you can see, it's very, very good. It nearly perfectly matches the true Bayesian posterior, which is very exciting to see. I will also briefly mention that in the original paper, we only showed this, but we've now expanded to doing 7 parameters. This includes multimodal posteriors, as well as the location of the sky that the gravitational wave comes from. So that's RA and DEC. So that's still in prep right now. I think we still need to fine-tune a few things, so the posteriors aren't brilliant, but we'll get better very, very soon. And yeah, the speed. So if you compare this to existing methods, whereas before it would take, hours to days to produce posteriors, now it takes of order a few milliseconds. So it's about 6 to 7 times order of magnitude speed up in performance, which is great. We can do more physics now. So some conclusions. We've shown, and so have other groups as well. I've done some follow-up work. A group at JPL did an alternative method using some parametric techniques. Green et al. At Edinburgh have also recently, in the past few weeks, also done a technique using normalizing flows. And I think we've all shown that variational inference is a very powerful tool for gravitational wave astronomy. Of course, in the future, we're trying to extend this to more realistic cases. So up the sampling rate. Also do this for signals containing matter, like binary neutron stars, because that's they emit light, so that's very useful. And our pipeline is called Vitamin. You can see it there at the GitHub link below. I will warn you that documentation is not that great. Everything's kind of in flux right now because we're working with referees at Nature. So yeah, I think we provided motivation for why we're doing this, what variational autoencoders are, and then finally talked about some of the results. As I said, the paper is on archive and is currently with referees. So, and that's some of the people that do ML and physics at Glasgow. There's me and Michael right there. Yeah, so thank you very much.
All right, questions for Hunter? Yes.
Hi, and this is congratulations. I mean, this is very impressive result. I have a question because it's often that people make lots of trial when designing such an algorithm, and there is a lot of the learning process that get lost because we get only the final point. So I'd be very curious to know how you come up with this structure and what really didn't work. If you can give some insight, that would be very useful.
Yeah. So the particular algorithm we used right there, that was definitely not where we started. We work on this for the last year or two. So we initially went on some really crazy routes. So one of them, we used a GAN. That didn't really work. Then we went from there to trying to use invertible neural networks, which have been shown to produce posteriors, but we just couldn't quite get the quality that we wanted from that. And then, we went over to a few people at the computer science department and showed them some of the work that we were doing. It turns out people that we were basing a lot of our work on were some of their competitors. And they said, why don't you try this? And it ended up working right out of the box, which was very, very fortunate. And it's also derived from first principles, which is also kind of a very nice, it's very, very nice mathematically. So that was sort of the route that we took. We have also had to make additions on top of what some of the computer scientists have already done with their work on recent and previous papers. So for example, with the sky localization, so right ascension is a wrap parameter. So we've had to implement some of the latent space distributions are wrapped distributions, so we use von Mises distributions. And then we also, in order to get the multimodal posteriors, it is very helpful to use a Gaussian mixture model approach. And which encoder was that? Encoder 1. So we implement a Gaussian mixture model approach in encoder 1 in order to get these multimodal posteriors, which we struggled with for quite a long time. And that was only really a recent development that we made in the last few months. So yeah, that's sort of the general approach that we took. But I'm definitely willing to go into more detail offline about how all the maths behind this works later.
So this is what you show works for Gaussian noise, right?
Yes.
Did you perform some tests for realistic data, the realistic noise?
So that would be a good next step, I think, going forward, is to use real detector noise. Though for our development purposes, we just decided to go with Gaussian noise because it's very easy to generate lots and lots of signals in Gaussian noise.
Yeah, so a follow-up question would be contamination with something that is non-Gaussian, so the transient glitches and so on. How did it perform on such things?
Yeah, so that would be very, very interesting to look into next, and somebody should do that. That would be a good paper. Yeah.
Last question.
Do I understand correctly in that you have actually a generator network? You're training an encoder and a generator in your model?
So define.
In your plot of your model, the D triangle here is
it's decoder. Yeah.
It's actually a neural network.
Yes. Yeah.
So all right. So are you not making your problem more difficult than it needs to be? Because the only thing that you care about is the latent space, no?
So the latent space informs sort of the shape of the posterior as well, right? So it's you kind of you can't just directly sort of get out of like the encoder sort of the posterior. It's
Okay. So it's like what's it outputting is the posterior itself or sample of the posterior?
So a sample from the posterior.
Oh, okay.
Right. Yeah. So if you sample from different parts of the latent space, you get different samples from the posterior.
Got it.
Yeah.
Okay.
So I'm not sure to not understand, but we had great discussion this morning about how all those Bayesian algorithms were, like always the true posterior was like coming from the basically the MCMC samplers. So would you say that now you're comparing it with the, like, you call it yourself the true posteriors, but would you with the new detection say these are the posteriors and you can just believe my algorithm is these are the true ones, or would you still say we still need
Oh, I definitely still think we need to use MC and nested sampling. I'm definitely not advocating for totally replacing those. But the way I kind of envision this being used is as a first sort of step, right? It's kind of, I wouldn't say replacing Baystar because I don't want to anger Baystar people. That's a very fast Bayesian posterior maker. But so I guess we would kind of replace Baystar in that this would be the initial alert you would send out to astronomers. And really the only limiting factor at that point is not generating the posteriors, but rather how fast can you tell the astronomers where to look, and then how long does it take them to actually swivel and point in the sky. But then I would then want to follow up with other sampling techniques to be sure, absolutely sure, that these are the right posteriors. So.
All right.
Very nice talk. For me, one of the real strengths of this that I see is, as you said, you struggle with getting the multimodal posteriors for quite a long time.
Yeah.
And I think that's a feature of every sampler.
Yeah.
So for me, one of the real strengths of this is that if this was to replace Baystar, having the information beforehand of how many modes you actually need to explore could allow you to make the choice between a simpler or more detailed sampler.
Yeah.
Because if you have a simpler sampler that works brilliantly with unimodal distributions, you can basically stick that in and get the inference running quicker.
Yeah, yeah, and that is definitely the case. I mean, this definitely works very, very, very well for unimodal posteriors, and even when you have a multimodal posterior, it will end up just trying to span the two modes if you don't use this Gaussian mixture model approach. But yeah, I think we're very, very close to getting this working really well. I mean, yeah, you can tell with the declination, it's not really there, but I think we're close to making that step. So, yeah.
All right, I guess we have to stop here. Thank you again.